So in the last video, I started talking about the index of refraction. So we've already discussed index of refraction. Oops. Index of refraction as it relates to the optical density of the medium. And we said that variable n represents the index of refraction, and a high n equals a greater optical density. In other words, light will travel slower through that medium. And we defined it as the ratio between the speed of light in a vacuum over the speed of light in the new medium. Okay. So now I want to move on to talking a little bit more about what refraction actually is. So refraction is simply the bending of light that is reaching an interface at an oblique angle. Okay, so light bends when it is shown at an interface at an oblique angle relative to the normal. Sorry, oblique angle relative to the normal. So remember, the normal is that imaginary line that sits perpendicular to the interface. So we will have two media. So we'll have medium 1 on one side of the interface and medium 2. So let's say that medium number 1 is air, and let's say medium number 2 is lucite. Okay. Now each of these different media have their own index of refraction, as is given by your reference table. And here are some indices of refraction. So here we have air, which has an index of refraction of 1.00, and lucite, which has an index of refraction of 1.5. So I'm going to write those values down. I'm going to say N1 is equal to 1.00, the index of refraction for air, and N2 is equal to 1.50. Okay. Now, we're going to shine the light at an oblique angle relative to the normal. So I'm going to draw in my normal right over here. We know this is the normal because I've drawn it sitting perpendicular to the interface, right? Here's the interface, or the line that separates medium 1 and medium 2. So here is my incident ray, which I'm going to label the incident ray. And that incident ray is at some angle, theta 1, or the angle of incidence relative to the normal. Well, I'm going to call that angle of incidence, I'm going to call it 30 degrees. So I'm going to say I have shown a light at a 30-degree angle to the normal. Well, if I want to predict the way that this light is going to bend from the air into the lucite, I can use a tool that is called Snell's law. So Snell's law states that N1 sine theta 1 equals N2 sine theta 2. And so given the index of refraction of medium 1, 1.00, sine, and given the angle of incidence, which I've defined as 30 degrees, and given that the second medium is lucite, which has an index of refraction of 1.50, we can solve for the angle of refraction, or the amount that this light ray is going to bend. So let's do that right now. So we have 1.00 times sine of 30. We know that sine of 30 is 0.5, but you can confirm that in your calculator. So 0.5 times 1. So this whole side of the equation comes out to be 0.5 is equal to 1.50 sine theta 2. So now I divide by 1.5, divide by 1.5, take the inverse sine, right? So theta 2 will be inverse sine of 0.5 over 1.5, and you should get, if you use your calculator in degree mode, you should get that theta 2 is about 19.5. 19.5 degrees. Okay, well what you'll notice is theta 1, which was 30 degrees, is bigger than theta 2, 19.5 degrees. So actually what's happening is this light ray starts out further away from the normal, but once it passes through this interface into the lucite, it's going to sit closer to the normal. There's our theta 2, and that's it. Okay, so this is refraction, and the reason that the light is bending at this interface is because it's changing speed, right? In this first medium air, n equals 1. The index of refraction is 1. So n equals c over v tells us that if n equals 1, then v, or the speed of the light in the air, must be equal to the speed of light in a vacuum. On the other hand, n equals c over v down here, we can actually calculate for how fast the light is traveling in the lucite, and I want you guys to do that one on your own. So I'll set up how you would find the speed of light in the air, right? So 1.00 is the index of refraction. C is always going to be 3 times 10 to the 8 meters per second. Over, we have an unknown speed of light in the medium air, but we know v times 1 is just going to be v. So v is going to be equal to 3 times 10 to the 8 meters per second. So now on your own, find the speed of light in lucite. Actually, sorry. Find the speed of light in lucite. So using n equals c over v, so everyone do it. N equals c over v, in other words, 1.5 equals 3 times 10 to the 8 meters per second over an unknown speed in lucite. So essentially you're just dividing out 3 times 10 to the 8 meters per second by 1.5, see what you get, and that will be the speed of light in lucite. I'm not sure why it's going in and out of focus. Okay. Very strange. My phone's having issues. Oh, that's better. Okay. So anyway, this is like an introduction to Snell's law. So Snell's law, we're going to do some other applications of it, but here is the basic formula, n1 sine theta 1, right, where n1 is the medium, so in this case it was air, and the associated index of refraction, 1.00. Theta 1 is the angle of incidence, so we can label theta 1 as the angle of incidence, right? Theta 2 is the angle of refraction, since we're talking about now the bending of light. And N2 is, of course, the index of refraction of medium 2, which is the lucite. So that's 1.50 based on our little chart over here. You have a chart in your reference table. This is actually my own chart, but I believe it's on maybe like the 3rd page, if I'm not mistaken, but I could be wrong. Okay, so that is Snell's law, and it's just a way of us predicting based on whatever media we're presented with, predicting the way that the light is going to bend when it strikes the interface. Now, one point I just want to make really quickly is that, again, if light is shown directly on the normal, it will not bend. It will pass straight through. So if you place a laser right where my pen is at 0 degrees to the normal, the line that the light will follow will always be 0 degrees to the normal, meaning once it passes into the new medium, the lucite, it will not bend at all. And that's because when you shine the light straight on, the entire wavefront is going to reach the boundary at the same time. So it will all change speed at the same time. However, when you shine light at an oblique angle, what happens is this. Your wavefronts will reach that interface at different periods of time. So the parts that reach there first will change speed first, while the rest is still traveling at the original speed in the first medium. So that's what causes the light to bend. Okay, so I hope that's helpful.